Okay, so it should be no surprise to you that since we have sum and difference identities for cosine, then we also have sum and difference identities for sine and tangent. So here's our sum and difference for both of these things. We're not going to talk about where they come from right now. And I will say again, like, you don't have to memorize these things. We just need to know how to apply them. And we need to know the difference between when we actually have a function that's on our unit circle versus when we have reference triangles like we did in the last example. People tend to mix that up a little bit where we are like either evaluating sine of 30 degrees or we actually know that the sine of A is some fraction, some ratio. So you need to know the difference between the two. But in general, I don't think that sum and difference identities are really that hard. They're a little bit tedious because we have a lot of things that we're calculating and it can take a little bit of time to like figure out what the two angles are that would combine to give these values. And like we have sum and difference identities, and then later on this chapter we'll talk about double angle and half angle identities. So there's lots of different combinations that we're going to do to this chapter that basically just try to get values of sine and tangent and cosine that aren't our normal unit circle values, but there's some combination of it. Like 75 degrees we saw was 30 degrees and 45 degrees, and we can use those combinations to come up with our new sine and cosine values of those things. So like we said last time, if we do have exact trig values, then the sum and difference can be defined as an exact trigonometric value. So even though we can type this in our calculator and come up with an approximation, we can find an exact value for it because we know that sine of 75 degrees is really the sine of 30 plus 45. And remember, we can't actually like distribute that sign throughout. These aren't parentheses that we do that. Sine is a function, so we're taking the function of something. It's like we can't distribute a square, we can't distribute a square root. Those are all functions of that. But we can find this in a different way by applying the sum and difference. So since this is a sum, I'm going to write out the sum formula above. And this would be our A and our B value. So really what that means is that we're looking for the sine of 30 times the cosine of 45 plus the cosine of 30 times the sine of 45. So we have two reference triangles that we're looking at. We're looking at a 30-degree reference triangle and a 45-degree reference triangle. We know in a 45-degree reference triangle, our values are root 2 over 2. So that's what we're going to replace in this section here. Cosine is root 2 over 2. Sine is root 2 over 2. Can't really see that very well. Maybe switch colors. And the next one for our sine value across from 1/2 is, or across from 30 degrees is 1/2. And then that means that our x value for that one is going to be root 2 or root 3 over 2. So that our sine value is 1/2 and our cosine value is root 3 over 2. So this should look really familiar because we did something really similar to that for cosine. So our first fraction multiply across, we get root 2 over 4, and our second fraction multiply across, root 3 times root 2 is root 6 over 4. So altogether in one fraction, since we have the same denominator, is root 2 plus root 6. And again, we don't have to use our calculator to check, but I'm going to. I'm going to find then the sine of 75 degrees, and it is approximately 0.9659325. And I'm going to find then the value of root 2 plus root 6, all divided by 4, and voila, we get the same approximation value. So these things are exact. And this would be like the decimal representation of it, but we can find an exact answer, so we want to represent it as an exact answer. So that should be like pretty easy because that's what we did for sine and cosine. What we haven't done too much yet is dealing with radians, and tangent's actually a little bit more complicated because there's a lot more going on in this, and we have some fraction. And so usually when we have fractions like that, especially since we're dealing with roots, we're going to have to rationalize it. But our first thought is trying to like figure out what things are on the unit circle that would either add up or subtract to this. So I'm going through my unit circle identities. I know that I have pi over 6 values. I know I have pi over 4 values. I know I have pi over 3 values. So I'm trying to figure out what would give pi over 12, or 7 pi over 12. So let's see, if I have pi over 4, that's 3 pi over 12, and pi over 3 is 4 pi over 12, so that one works. So I can break this down into 4 pi over 12 plus 3 pi over 12. And 4 pi over 12 is pi over 3, and 3 pi over 12 is pi over 4. I was going to switch colors because you can't see my blue. So this would be my A and my B. So again, I'm using now the sum formula for tangent, so I'm going to write that down here. So my sum formula is A plus B, tangent of A plus the tangent of B, 1 minus the tangent of A times the tangent of B. So it's definitely a little bit more complicated. There's definitely a lot more simplification that needs to happen when we find these values. So we'll have the tangent of pi over 3 plus the tangent of pi over 4, 1 minus the tangent of pi over 3 times the tangent of pi over 4. So remember, pi over 3 and pi over 4, you can convert that into degrees if you want to, or maybe you remember. So pi over 4 is an easy one to remember. That's a 45-degree angle. And pi over 3, remember, it's kind of like opposite. So like every time we have pi over 6 or pi, then we're representing like a 30-degree reference angle. Pi over 3 would be a 60-degree reference angle. So that's what we're looking at for R2. We have pi over 3, which is 60-degree reference angle. Oops, sorry. And pi over 4, which is a 45-degree reference angle. Okay, so this is 60 degrees. We have root 3 over 2, and then 1/2. So the tangent of pi over 3, or tangent of 60-degree reference angle, would be this value sine over cosine. The 2's will cancel out. We're left with root 3. And then in a 45-degree reference triangle, we have root 2 over 2, so the tangent of 45, or the tangent of pi over 4, is root 2 over 2 over root 2 over 2, so that's just 1. Okay, so we'll evaluate. I'm going to write this down here because I'm going to need a little bit more room. So the tangent of pi over 3 is root 3. We just found that. The tangent of pi over 4 is 1. The tangent of pi over 3 again is root 3, and then the tangent of pi over 4 is 1. So altogether we get root 3 plus 1 over 1 minus root 3. Now in general, that's not something that's simplified because we have a radical in the denominator. So in general, we have to rationalize. The rationalization process for this is a little bit different because before, when we've rationalized, we've just like multiplied by like root 3 over root 3, and then it all worked out because root 3 times root 3 is 3. This one's a little bit more difficult because we have this 1 here. So we can't just multiply by root 3 over root 3 because we'd have to distribute that root 3 and we'd still be a root 3 in the denominator. So you probably remember this from Algebra 2, and we just kind of talked about this recently when we were doing all of our identities. The thing to do here is to multiply by the conjugate. So the conjugate in the denominator, it's always dealing with the denominator. You change the sign, so instead of 1 minus root 3, it's 1 plus root 3. So we multiply top and bottom by that. Now in the denominator, I'm going to write it over here so I don't have to rewrite it. When I multiply all these things out, the cool thing about multiplying by the conjugate is that it does rationalize. It gets rid of those middle terms. This minus and this plus, our root 3's will cancel out. we'll have 1 plus root 3 minus root 3, and then minus root 3 times root 3, which will just be 3. So these things will cancel out. I'll have 1 minus 3 or negative 2. So that's all the stuff in the denominator. Now you don't have to show this work every single time. Like, you should know when you multiply by the conjugate that it's only going to be 1 and then minus 3, because those root 3's and root 3's will cancel. And you don't have to like show this middle term, but just for the process of like going through this, I'm going to do that I'm going to show you this once, but I won't do that every single time. I might do it in my head or say it out loud, but you don't have to go through that process. You should know that it's just going to be the first terms and then the last terms, because the middle terms will cancel. So I'll have negative 2 in the denominator. We do have to multiply this one out because we don't have things that cancel. So I'll have root 3, well, I'll do it this way. Root 3 plus 3, root 3 times root 3, and then plus 1, and then plus root 3. So if I combine some like terms on the top, I have 3 and 1, which is 4, and root 3, which is 2 root 3. And then the last step of this problem, since 4, 2, and negative 2 are all divisible by 2, I can divide each of these terms. So I can divide the 4 by negative 2, and I get negative 2. And I can divide the 2 by negative 2, and I get negative 1. So my final answer is negative 2 minus root 3. Now I just want to warn you right here that when you do split this up, sometimes you might be tempted, like if this were like an 8 in here or a 6, you might be tempted to divide the 6 by negative 2, but you can't do that. You only do whole numbers. So the 2, whatever's out front, is what you're going to divide. Now, just because we've been looking at approximations and we're seeing how good our exact answers are and making sure that we did something right, which is kind of the cool thing about this chapter, is that most of the time you can see if you did it right. We are looking for 7 pi over 12, which is in radian mode. So I'm going to go back to my calculator and change to radian mode. And I'm going to evaluate tangent of 7 pi divided by 12. And I get negative 3 point whatever. And I'm also going to then approximate this or find this answer in my calculator. And there we go. We get the same answer. So we know we did something right. We know we found the actual exact answer at the end. So it's kind of nice that you can go back and check. And that means that if you didn't get this right, then you did something wrong here in your simplification, or maybe you had a negative when you weren't supposed to, or maybe you added instead of subtracting, or something along those lines. Okay, 2 more. Tangent of 5 pi over 12. So again, we are going to try to see if we can break this up into some things that we can come up with to either add or subtract to 5 pi over 12. In my mind, I go through all the processes of like all the pi over 4 and pi over 3 and pi over 6 and put them in terms of pi over 12, so that way I can come up with a combination of it. So if I change this into pi over 12, I would multiply top and bottom by 3, so 3 pi over 12. This one I would multiply top and bottom by 4, so 4 pi over 12. That's how we got the 7. And this one I would multiply top and bottom by 2. So I get 2 pi over 12. So I'm looking for a combination of 5, so I can split it up and use the sum identity for 3 pi over 2, or 3 pi over 12, and 2 pi over 12. That might not be the only way to do this too. There might be other ways. Like I could say, instead of pi over 3, I could look at 2 pi over 3, which I multiply both top and bottom by 4, and you get 8 pi over 12. So I could do like 8 pi over 12 minus 3 pi over 12, or 2 pi over 3 minus 4 pi over 4, and use the difference identity, and I should get the same answer. It's really up to you. If you want to, like, I would maybe stick in the first quadrant if you can, because those are all positive values, and you have a better chance of like making a mistake if you're dealing with 2 pi over 3, which is in quadrant 2, and your cosine's negative, and you might draw your reference triangle wrong, or you might forget a negative here and there. But you should get the same answer. It's really a combination of it's really just some sort of combination of what you want. So I'm going to use these two, because these two are going to give me my 5 pi over 12. So tangent of pi over 4 plus pi over 6. So again, I'm using my sum identity there, which is 1, or tangent of A plus tangent of B over 1 minus tangent A, tangent B. I'm going to double check to make sure I got that right before I do this whole problem. Tangent A, tangent B, 1 minus 2. Okay, we're all good. Okay, so I need to find the tangent of pi over 4 plus the tangent of pi over 6, 1 minus the tangent of pi over 4 times the tangent of pi over 6. Well, the pi over 4 we just found on the other side. Pi over 4 is 45 degrees. The tangent's just 1. So we need to figure out what, this is what we have so far. We just need to figure out what the tangent of pi over 6 is. So pi over 6 is a 30-degree reference angle. So this is 45 degrees. This is 30 degrees. And I don't care if you want to like transform it into degrees and then find all these things in degrees, and then like you can even make this into degrees, so that's really looking for the tangent of 75 degrees. That's fine, and you can stick all in degree mode. That's an okay thing to do. I just want to, like, right now we're just dealing with radians, and we're usually pretty bad at radians, so I'm going to stick with radians so you can get a little bit more practice. But if you want to do it all in degrees, go for it. So this is 1/2 and root 3 over 2. So my tangent of this 30 degrees, which is pi over 6, is going to be 1/2 over root 3 over 2. When I multiply by the reciprocal, I'll have 1 over root 3, which, remember, when we rationalize, will be root 3 over 3. Ew, that's ugly. Okay, so we got to simplify. This is where the hard part comes in. So on the top, I have 1 plus root 3 over 3. On the bottom, I have 1 minus root 3 over 3. Last chapter, when we had fractions within fractions, the thing to do was to find a common denominator in the top and the bottom. So that's what we're going to do. So this 1, we'd multiply by 3 over 3. So we can kind of ignore that now. So now I have 3 plus root 3 over 3, 3 over 3 minus root 3 over 3. So altogether that becomes 3 plus root 3 over 3 and 3 minus root 3 over 3. And now when we had, again, like when we had fractions and fractions, the next step to do to simplify this thing was to multiply by the reciprocal. So that's what we're going to do. Flip this thing around. Our 3's cancel, top and bottom. So we're left with 3 plus root 3 over 3 minus root 3. And we're not done yet. We have to simplify this a little bit, multiply by the conjugate. So we should multiply by 3 plus root 3 and 3 plus root 3, since we have a 3 minus root 3 in the denominator. Again, when we actually distribute all this out, the middle terms will cancel, so it's really just the first term. So 3 times 3 is 9, and then minus root 3 times positive root 3. The root 3's will cancel into 3, and we'll have a minus 3 then. So it should be over 6. That's in the denominator. On the top, we'll have 9 plus 3 root 3 plus 3 root 3, so plus 6 root 3, and then plus root 3 times root 3 is 3. So altogether we get 12 plus 6 root 3 over 6. And this thing can simplify down because everything is divisible by 6. So 12 divided by 6 is 2. 6 divided by 6 is 1. So you get 2 plus root 3. Kind of amazing that that whole thing simplifies down into something pretty simple. And I'm going to double check again with my calculator. So I know I'm looking for tangent, let's make sure I'm in radian mode. Okay, tangent of 5 pi over 12 and 2 plus root 3. There we go. Now again, I told you that you could really, since we talked about it in degree mode and we found that this was 45 and 30, you could find then the tangent of 75 degrees, and we should also have the same problem. Just make sure that you know like what mode you're in, whether you're doing it in radians means that you need to have your calculator in radians, but I just found this tangent of 75 degrees, so I just switched the mode of my calculator back to degrees. You just have to make sure that you know what you're doing, so you're consistent, so when you check your answer, you know that you did it right. Okay, last problem, and then we're good to go. This is like the last example that we did in the sum and difference for cosine. We're going to find it all for sine, or sum and difference for sine, sum and difference for cosine, and the sum and difference for tangent, all in the same problem. So again, last time when we did the sum and difference for cosine, we drew two different reference triangles because we're dealing with two different angles here. We're dealing with angle A, whatever that is, and angle B, whatever that is. It tells us that A is in quadrant 2, so here's my reference triangle for A. This is angle A. And B is in quadrant 3. So angle B. Okay, so I'm going to come up with my whole list here. So we're going to look at for the sine A, cosine A, tangent A, sine B, cosine B, tangent B. So the sine of A is 4 over 5. So opposite over hypotenuse. This is a 3, 4, 5 triangle, so that's nice. We don't have to use Pythagorean theorem. So this value here is going to be 3, but remember you're in quadrant 2, so don't forget your negatives. So our cosine is then negative 3 over 5, and then our tangent's going to be negative 4 over 3. Remember how particular I was with negatives back in like chapter 1 and chapter 2 and chapter 3. It's coming back, so be careful. Watch your negatives. They'll get you. And the cosine of B is negative 5 over 13. It's a 5, 12, 13 triangle. So this value here is going to be 12, which is going to be negative. So I get negative 12 over 13, negative 5 over 13, and then negative 12 over negative 5, which is going to be positive then 12 over 5. Okay. So we're going to find all the exact values of sine of A plus B, cosine of A plus B, and tangent of A plus B. And then last but not least, we're going to look for the quadrant of A plus B, because right now we know A is in quadrant 2 and B is in quadrant 3, but we don't know the quadrant of A plus B. It could be a combination of any of those things. Okay, so the sine of A plus B, using our identities, is sine A cosine B plus cosine A sine B. Sine, oh wait, cosine A, right? Okay. Going to write it as sine B. Okay, there we go. That should be right. Sine A, cosine B, cosine A, sine B. Double check that. Okay, just making sure before I do this whole problem and get it wrong. So we're looking for the sine of A plus B. And we conveniently have all these things listed. I know my sine A is 4 over 5. I know my cosine B is negative 5 over 13. Remember, like, these are angles, these are ratios, so you're not doing like the sine of 4 over 5 and then typing that into your calculator. That's a mistake I see all the time. In these problems where you're actually given the ratio, you're replacing the entire sine A with this ratio. This is saying evaluate sine at this angle and you get these values. It's like if I do the tangent of 45 degrees, I get this ratio of root 2 over 2 over root 2 over 2, which is 1. Okay, same idea. Cosine A is negative 3 over 5, and the sine of B is negative 12 over 13. Okay, so let's simplify. 4 times negative 5 is negative 20. 5 times 13 is 65. Plus 3 times negative 12 is 36, and 5 times 13 is 65. So when we combine that into one fraction, we get negative 20 plus 36, which is 16 over 65. Okay, now let's do the cosine. So this was on the previous sheet. Cosine of A plus cosine of B is the cosine of A, cosine of B, minus sine A, sine B. That's the identity for it. Again, we have all these things, so we can just plug all that stuff in to our problem. So the cosine of A is negative 3 over 5. The cosine of B is negative 5 over 13. The sine A is 4 over 5, and then the sine B is negative 12 over 13. And now we can simplify. So just like above, negative 3 times negative 5, multiply across is positive 15 over, again, 5 times 13 is 65. For negative 4, or minus, I guess you could do it either way, negative 4 times negative 12 is going to be positive 48 all over 65. And then we add our fractions across, we get 63 over 65. So that's the sine of A plus B. This is the cosine of A plus B. Now we're going to look at the tangent of A plus B. Our tangent of A plus B, sum and difference is tangent A plus tangent B all over 1 minus tangent A, tangent B. Tangent A is negative 4 over 3. Tangent B is 12 over 5. 1 minus tangent A again is negative 4 over 3. And tangent B is 12 over 5. And tangent's always a little bit harder because we have to do a lot more simplification for it. It's not as easy as just like multiplying fractions that we have, because we have to like, what I'm trying to do here, I'm trying to move my pen. There we go. We have to find common denominators and tops and bottoms, and it's a little bit more complicated. So on the top here, if I was going to find a common denominator, it'd be 15. So I'd multiply this one by 5 over 5 and this by 3 over 3. And on the bottom, before I rewrite it in here, just because I want to save some space, I'd have 1 plus 48 over 15. So I'd have to find a common denominator and multiply this one by 15 over 15. So altogether, I'd have negative 20 over 15 plus 36 over 15. And on the bottom, 15 over 15 plus 48 over 15. So on the top, I get positive 16 over 15. And on the bottom, we get 63 over 15. And then when we multiply by the reciprocal, so I'd have 16 over 15 times 15 over 63. My 15s would cancel, and I'd be left with 16 over 65, or 63. Now, interestingly enough, maybe not so interesting, these values, or these like 16 and 33, or 16 and 33 shouldn't look unfamiliar, because we actually found those values up here with sine of A plus B and cosine of A plus B. So the other way, the easier way, like I just went through this way, and that's just one method, but an easier way of finding the tangent of A plus B since you know tangent is really sine over cosine, and we already found sine and cosine, we could just do the ratio of the things that we just found. So I know that my sine value is 16 over 65. I know my cosine value is 63 over 65. So when I flip that around and multiply by the reciprocal, my 65s will cancel, and I'll be left with 16 over 63. So you don't have to go through like this whole madness to come up with that. You do if you are looking for if you're finding just like the tangent of A plus B and you don't have anything else, like you could go through the process of finding sine and cosine and then find the tangent that way. that might be more work, that might be less work, I don't know. But you could do it both ways. And I prefer this way. Like I will almost, since I already found sine and cosine already, I will almost never do it this way. But you can, it's just more work, because why would I want to do more work? I think humans in general are innately lazy. I'm definitely a lazy person. If I already found an easier way, I'm going to pick that way, because why would I do something that's harder on myself when I can solve a problem quicker? Okay, we're not done yet. This is another part that we tend to mistake or miss, I guess, is we're actually looking for the quadrant too. We can't forget that. So the quadrant of a plus b. Well, to find a quadrant, I would look for like the angle measurement to decide if it's between 0 and 90 degrees, but we don't have any angle measurements, but we do have sine, cosine, and tangent. The sine of a plus b is something that's positive value. The cosine of a plus b is something that's positive. So really we're looking for where is sine positive, where is cosine positive. That happens there in quadrant 1. So the quadrant of a plus b is going to be 1. I'm home right now with Beckett. He's doing well. Come here, Beckett. Maybe I can show him. Beckett, sit. Good boy. There we go. Hi, Beckett. He's very happy right now. My cutie.